So the two main foundational concepts of statistics are variance and error. If you haven't seen the video on variance, go watch that one first. But so let's talk about error now. And now variance and error are the two foundational concepts, but error is actually a type of variance. So error is almost always present. Even when the measurements are super accurate, just the more accurate they are, the smaller the error is going to be. Sometimes it's a little bit more. I think it's safe to say we may be dealing with some voter fraud issues. That kind of carries a little bit different connotation more recently. But so the idea of error is basically it's always there. So statistics are designed to sort of account for error and to recognize it and to diminish it and as much as we can and things like that, because it's always there. It's like, so the entirety of statistics has to be designed around the fact that error is always there. And so statistics then are designed to tell us about error. How much error is there? Is there enough that it's going to basically wreck what we're trying to do, or can we still try to figure out what's going on with our data? So that's what statistics are kind of designed to do. So why is error important? Well, once we know how much error is present, we can make an informed judgment about the existence of whatever it is we're looking at. So do true differences exist? So that phenomenon or relationship, whatever it is we're actually interested in, it exists, it's there. That's an important question to know. Or are the differences most likely just measurement error? So the relationship probably doesn't exist. And that's kind of what statistics can tell us, that are the differences that we're seeing, because remember, we're always going to see differences. Nothing is ever going to be exactly the same, even if you're measuring the same thing twice. But are those differences real, or is it just error? And that's an important question we have to answer, because until we answer that question, we can't talk about that original thing that we're trying to investigate. So how do we know how much error is present? Well, the answer, by using statistics. That's what they're designed to do. So stats deal with variance, and they help to estimate the presence of error variance, which is one of the two types of variance. So from the variance video, we talked about real variance versus error variance. And so error variance is error. And so stats are dealing with sort of estimating, well, how much variance is error variance and how much variance is real variance. And that's what statistics do. So why is it so difficult to estimate error? Because it is. It's not easy. Well, measurement always has error. We know that. Estimates of error, though, are also a measurement on their own. And then they are going to have their own error. So we're trying to measure error, but that measurement itself is going to have its own error. And so it just keeps looping and looping, and then we try to measure that error. Well, then that measurement is going to have its own error, because measurements always have error. So that means that we can only deal with probabilities, and that's why so much of statistics is probabilities, because we can never have an exact number, because we never know how much error there is. We can guess, we can get really good guesses, but you can never be 100% sure about what, about how much error there is, and which means how much real variance there is. So that means we can only deal with probabilities of being correct when we're talking about true differences, or when we're making those comparisons and when we want to see significant differences, statistically significant differences. We can only talk about what's the likelihood, what's the probability. And so that's why we often have ranges. It'll be like we have like confidence intervals, and we have, well, here's a measurement plus or minus this. That's because we don't know for sure what a measurement actually is without sort of having to give our best guess. But there's always error. So the basic concepts in statistics then is this idea that error and variance, we can see them in a lot of different ways. So because error and variance don't look the same, if they always look the same, that would just be too easy, wouldn't it? So we have different types of statistics then to deal with different types of variance and to deal with different types of error. So you have different statistics to detect and evaluate your different types of error and your different types of variance. So then this begs the question, well, what makes a good statistic then? Well, there's two criteria for that. If we want a good statistic, we want, first of all, you need to be able to address the problem you're trying to address. You have to have enough accuracy to address the problem, because some statistics have more accuracy than others, and it depends on sort of what we're looking at. So for a statistic to be good, to be useful, it has to give a kind of quick and easy to understand mental picture of whatever it is you're investigating. And of course, this is all relative. You have to know a certain amount of statistics to be able to read these quick and easy mental pictures and understand what they mean. But it basically has to make things easier to understand and faster to see what's going on than, just going through raw data or some other statistics that might not be so helpful. So it has to be doing significantly better at basically showing us what's happening in a quick, easy to understand way, a summarized way. So you need that accuracy, but the criteria for accuracy, it's something that's called power is the first part of this. So to have an accurate statistic, it has to have enough power. And power is how good that statistic is at finding something that's there. So think about that. If there is a difference, if there is something real going on, we have some kind of treatment intervention for, let's say, issues with sexual deviance. And so there's a treatment for sex offenders and who have problems of deviant fantasies or something like that. And there's a specific treatment. So we want to see if there's a difference in their, ability to control their fantasies or whatever before the treatment versus after the treatment. We want to see if there's a difference there, because if the treatment is doing what it's supposed to be doing, there should be a difference there. They should be better after the treatment. So the power of a statistic then is the ability to find that difference. So if let's say for argument's sake the treatment works. We know somehow that the treatment does work. So that means there is a difference. They are doing better after the treatment. A good statistic with enough power is going to be able to find that difference and show it to us. So to have enough power means that we pick the right statistic to find a difference that is actually there. And of course, we don't know whether there is a difference there, so we have to rely on knowing that we've chosen the right statistic. So, but if it has enough power for what the question it is that we're asking, then it's going to be able to find a difference if it actually exists. And the amount of power that's needed is kind of tied to the importance of the outcome. So, for example, if we just need a basic overview of a relationship, like what's happening here? Do we need to investigate this any further? Then we don't need as much power in our statistic as if we want a more definitive answer, like what exactly is a relationship? How strong is it? How can we use it to predict behavior? If you want to start answering questions like that, you need more power in your statistic. And so then the other criteria for accuracy is robustness. And robustness is essentially every statistic, when you run, analyses and whatnot, every statistic has assumptions. Some have a lot of assumptions and some have very few. But all stats are essentially less and less useful, meaning they're more full of error, as more of those assumptions are violated and to greater degrees that those assumptions are violated. So the robustness of a statistic is how well it can do even if we have violated an assumption. So I'll give you an example. A very common assumption is that there is a normal curve happening in the population. So our sample, we're going to pull a sample from a population, and the assumption is that there is a normal curve, that the variable is normally distributed. And so if that's an underlying assumption, and our variable actually is not normally distributed, because that normal curve is that nice bell curve, if we violate that assumption, there are some statistics that can still do well. They're just a little bit weaker. You have to have a bigger of a difference for them to find it, but they can still do fairly well. But then other statistics, if you violate that assumption, you can't really use the statistic anymore. So if a statistic is really robust, it's still useful even if we don't have that nice normal curve, but it's so that it's less robust if you have to make sure you are not violating any assumptions of that statistic. So because violations of those assumptions can lead to results that are essentially just full of error. And we don't want that. We want to use the right statistic that has enough power, that is robust enough that, for whatever assumptions that we might have to violate based on the data that we have, we can't choose that. Either we meet the assumptions or we don't. We can't change our data to better meet the assumptions. So if there's some assumption that we have to violate, hopefully not too much. So if we're not a quite normal curve, maybe it's just skewed a little bit. But if it's like super skewed, then that may be problematic. We have to find a different statistic. But the more of those assumptions that we violate, then the more error we're going to have. So especially if the statistic that we've chosen is not robust. So to have a good statistic means that it's going to have power and it's going to have robustness. And if you have both of those, then you've chosen the right statistic.